Okay, I think we start. Let's see. Yeah, okay. So, good afternoon, everybody out there. So, today we have another one of our machine learning for science seminar. And it is my pleasure to introduce you to Volker Deringer from the University of Oxford. So for those of you who don't know Volker, he did his PhD in Germany, in Aachen, in inorganic chemistry, in fact. And then he moved for a postdoc position, actually two postdoc positions back-to-back in Cambridge, where he was essentially in the group of Gabor Chani, who gave a seminar a couple of weeks back. And then since late last year, late 2019, he took up a position in Oxford in the chemistry department. So, so it is a great pleasure to have him here. And today is going to talk about how to use machine learning potential to do real life chemistry, essentially. So, please.
Thank you very much, Stefano, for the kind introduction and for the opportunity to present in this very interesting series. It's the first time I'm giving a virtual seminar like this. And I thought the title of this ML4Science is a really exciting thing, because we're now at a stage where not only is the community really excited about machine learning approaches, but they are starting to be used for actual research problems. And this is one of the areas where I want to talk about today, is the question, how can we use machine learned potentials to solve problems in materials chemistry? Now, there have been great presentations already in this series about machine learning interatomic potential, so I can really go through this quite quickly, but I still wanted to give a short overview of the techniques that people, and that also my new group at Oxford, are using. So when I talk about materials modeling, I mean that we want to describe the potential energy surface of a given system. So essentially, we want to know the energy and the forces as a function of where the atoms are. So if you sketch this in a very schematic way for carbon, you'd have diamond in a local minimum here, you'd have this nanotube in a minimum bit higher up. And it's no problem to compute very accurate energies and forces for selected structures, but it is very difficult to sample the entirety of this potential energy surface because quantum mechanical computations are so expensive. Now, an approach that has come up really over the last 10 years, give or take, is the thought to use a very initially non-chemical approach, and to think of this potential energy surface as just a very high dimensional function that I want to accurately fit. And the key in machine learning is that I'm doing this fit without any physical knowledge about how the potential energy surface really looks. But instead, I'm aiming to extract all that information from the data points that I have. So these bullet points here. And the idea is now, based on properly chosen reference points, to describe the potential energy surface. And once I have that, I can do all sorts of modeling things with that. This is one area, of course, where machine learning is being used, and there are multiple others. And there's so much exciting work going on that it's very hard to even keep up with the literature. There are a couple of very nice overview papers that I really like, where other applications of machine learning methods, both unsupervised and supervised, are being discussed. And I won't talk about this today. Instead, I want to focus on the question, what do you need to make a machine learning-based interatomic potential or force field? Notice figures taken from an overview paper that we've written last year. So essentially, you need three ingredients for machine learned force fields. You need, first of all, you need data. You need properly chosen reference configurations to which you make the fit. And because you only need a few hundred or thousand of these configurations, you can evaluate them accurately with a quantum mechanical method. Once you've built this database, you need a way to describe the atomic structure. And there have been seminars before in this series where you've been shown about how to encode these atomic environments. And the third part is then the regression or the fitting task itself. And very, very generally, there's three major types of methods that are in active use today. So the first, artificial neural network potentials, that was pioneered by Jörg Biller, who's now in Göttingen. And now there's multiple variants that are very widely used. There's kernel methods, which are based on atomic similarity functions, and I'm going to talk about these in what follows. And there's linear fitting, where you choose very carefully defined local functions and then combine them linearly and make a fit. All these three types of methods are in active use, and there are benchmark studies coming out that are telling us that all of them are really, really powerful in modeling materials. So I'm going to talk a bit about the GAP methodology that was developed by Gabor-Gianni and his group at Cambridge, where I held 2 consecutive fellowships over the recent years, and we've been working a lot on using these methods for materials problems. So here's one of the problems that I find quite exciting. That is amorphous carbon. So the chemists know this way of talking about sp, sp2, and sp3 atoms depending on the coordination numbers, and you can have all these types of environments in amorphous carbon depending on how dense you make the sample. And I remember when I had just arrived at Cambridge, I probably spent a week just in the library reading this book here and finding out all the exciting things about amorphous carbon, and it's been with me ever since. So in terms of the first ingredient, how do you make reference data? Well, you can do small-scale molecular dynamic simulations, and this is in fact a DFT simulation here, where you take a box of atoms, you randomize them at very high temperature, and then you simulate the melt and then rapidly cool it down to room temperature. And you see by the color coding, which indicates the coordination numbers, that the local structure changes massively in that process. So that already tells us it is a huge challenge for computations to accurately describe all these different types of atomic environments. The initial rounds of that can be done with DFT-MD, but then once you have a decent potential, you can then run more simulations with those and gradually grow your reference database until you're happy with what is in it. The second ingredient, I'm just going to skim this, but I wanted to write down the equations once. This was developed by Bartok and Gabor-Gianni. This is the smooth overlap of atomic positions. It's one way of representing and in fact comparing atomic environments. So if I wanted to describe the neighborhood of this atom here in the center, I would place Gaussian functions on each of the neighboring atoms up to a certain cutoff, and then just look at the neighbor density, which is a sum over all these positions. And now to compare 2 different environments, which is what I need for kernel methods, I'm going to integrate over these densities, and I'm going to integrate out the rotation. So if 2 atoms are oriented like this or like that, they will be giving you the same value. And the slope is defined in such a way that it is going to give you a measure between 0, which means completely dissimilar, up to 1, which means identical, up to a cutoff, and up to rotation. So in practice, how do you do this? You don't solve the integrals in the way that's written on the left, but you expand the density into a local basis with radial and spherical terms. And again, the chemists will recognize that this looks very, very similar to the way that we're building atomic orbitals in the first year lectures. You then go and take the coefficients of this expansion and combine them into a dot product kernel that is really efficient to evaluate in practice. Sometimes you need a bit more than that, and this is an example from a potential that we've made for amorphous carbon mainly. So what I'm showing you here is a scan of the potential energy of just two carbon atoms in vacuum terms of placing closer and closer together. Of course, this is from DFT. So we'll have some minimum if we bring the atoms close, and then if we bring them too close, they're going to be repelling. So if I try to make an ML potential just using a many-body term, which in this case is SOAP, which could be any very flexible many-body term, I'm going to get a potential which looks like this. So it's really, really good in the area where the interactions are bonding. But over here, it's going to be quite bad. And if I try to run simulations with this potential, you can imagine it's not going to be very, very good. So, and that's, of course, a consequence of the fact that this descriptor is so high-dimensional and is so flexible, and it's going to do something here because it hasn't seen any data. So an alternative would be to say, can we fit a model just based on pair interaction? So we can define a descriptor that is just dependent on pairs of atoms. And you see this one, it does get the repulsion correct. It's not so great in the region further away because it is really there to capture the broad features of the potential energy surface. We've then experimented with various combinations. So we mixed in a three-body term. This is again for carbon. And then if you combine the two-body, three-body, and the SOAP, you get a good potential model. So the third thing that you need, so again, drawing up this picture here, we've talked about the reference data, we've talked about descriptors, and now we need to do the fit itself, which here is done using gap regression. So we're comparing essentially, using these kernel functions, we're comparing a new environment with those that are already in the database. This is again taken from our overview article. And the whole framework was introduced really in 2010 already by Albert Bartok and Gabachani. So what we've done here for carbon is really this combination of different types of models. So we have a two-body term here, and then we have a three-body and a many-body model, and they're combined by proper scaling factors. So you need to scale them appropriately. The largest amount of the interaction energy is actually represented by the two-body term, and then the three-body and many-body term gradually add to that picture. Here's the expression for the energy, where we have, again, these kernel functions that I just talked about. The regression parameters are what I determine when I make the fit, and then once I have those, I can evaluate the energy and also the forces for any new configuration that I might be looking at. All right, so what I really want to focus on here is the question, how can we use these methods to solve problems in materials chemistry? And so picking up from the title of the series, I say, okay, what about ML for chemistry? What can you do for my own research? And I want to basically make three statements that I want to support with data. So my first statement is that these potentials are accurate. And by accurate, I mean they give me realistic structure models of complicated materials that are consistent with all the experimental evidence, that allow me to have confidence in what I have actually computed. So again, looking back at the carbon potential, I quickly wanted to talk about how do we validate potentials. Now, one thing to do is to look at energy and force error. So you see here the ground truth computed from DFT for lots of different carbon configurations, and you see here the prediction from the potential that we've made. You see that the overall agreement is quite good. It is not perfect, and that's quite important to stress, right? There is still a bit of scatter around the diagonal. So the most pressing question is, what does that mean in practice? How does it affect properties that interest me? So here's something that is quite useful as a benchmark, because we have access to experimental data, that is the Young's modulus and other elastic properties. So here, these different symbols are all experimental references, and the red line is our ML potential. In black, we've got one of the best empirical interatomic potentials, which is really good and has been used for important applications, but which can't quantitatively capture these subtle things. The other things I've shown you these quenched carbon structures where we do molecular dynamics at crazy high temperature and cool the structure down very fast. But this is not how you make amorphous carbon in reality. This is what you do. You take a surface and you shoot atoms at this surface one by one. And this is what we've done in ML-driven simulations. And this is work that was done by Miguel Caro in Aalto University, who's now one of my most long-term and most productive collaborators. So he's basically taken the potential and thrown atoms at a surface. So you're looking at about 10,000 atoms computed at quantum mechanical accuracy, deposited one after the other. And we've very recently put up a preprint on arXiv, which has all the details of how to do that and all the recipes and all the technical aspects. And what does that give us? That gives us films which are consistent with what people have seen in the experiment. So the quantity to look at is the count of sp3 atoms, or fourfold bonded atoms, in the center of the slab. And these cuts here are basically done along the slab. So at the bottom we have the template, which is graphite-like. This is the shaded area. And then we have the center of the slab where the atoms are really tetrahedral-like. So they're reaching up to 90% sp3 count. This was something that was impossible to achieve with simpler empirical potentials. So this was quite exciting, and it allowed us to look a bit at the mechanism by which these films actually grow and all that. Another amorphous material, if you want to study amorphous materials, you often come across amorphous silicon, which is one of the textbook cases. So amorphous silicon is locally quite similar to diamond, and it's done just very disordered on the longer scale. So you see all sorts of distorted tetrahedra, and you see almost all of the atoms in fourfold coordination, but there are a few which have either 3 or 5 neighbors. And it turns out that these defects are quite important for the stability of the material. How have these been made? Again, this is a quench simulation where I'm taking a liquid and I'm cooling it slowly to the amorphous state. In this case, I'm doing the quench over a much longer time scale. And it turns out, if I go and look at the stability of these samples as I cool them down at very different rates, so you see up here 10 to the 14 Kelvin per seconds down to 10 to the 11. 10 to the 11 Kelvin per seconds means a simulation time of 10 nanoseconds. So this is still quite fast, but it does come close to what people measure in calorimetry for properly annealed amorphous silicon samples. So this was quite encouraging. Another property that you can use to test these structures is solid state NMR. So these are predicted 29 silicon shifts for, again, structures cooled at different rates, and only if you cool very slowly, which you can do with ML potentials, so you can't do it easily with DFT, then you get something that really nicely matches the experimental datum. The last thing to look at is the structure factor from diffraction. So you see here the height of the first sharp diffraction peak is a measure for how ordered your sample really is. And here we've got the gap. So this is the ML-driven simulation in blue compared to some of the best very, very large-scale models out there. And we do really, really well, even if we just use 4,000 atoms in the set. Does look really, really nice. The other thing we can do, if we have an accurate description of the structure, is that we can try to understand a bit better what are the subtle details that make up this amorphous system. So what I've done here, I've color-coded a few atoms from an amorphous silicon structure according to their local energies. Now, you remember in the equations I showed before, I've said there are local energies of individual atoms that we're then summing together. So I can look at the local energies and say, how are they correlated with the local environment? And are atoms in more favorable configurations more stable? And this little picture does suggest that it is so. So we've got an atom in an almost perfect tetrahedral-like environment, very low in energy, a distorted tetrahedron atom is higher up, and then we've got this defect here with a high local energy. And of course, this is one snapshot, but you can go and look at the distribution over the whole of the cell, and you're going to see that if you cool very fast, you still have a lot of high energy environments there, but if you cool it slowly, you get something where the center of gravity is quite close to the experimental excess enthalpy, and we can quantify the error of the prediction. I won't go into details, but it does show us that the predictions are really, really accurate. We can then go and start looking in a bit more detail at the role of each of these atoms. And this is now a two-dimensional plot of the structural similarity to ideal diamond-type silicon. So basically, the further to the right the points are, the more diamond-like the atom is. And then on the vertical axis, we've got the local energy from the ML model. So you see that most of the fourfold atoms follow this rough trend here. The threefold atoms are quite defined in how their local structure is, a single distribution here, and they are high in energy, as people have previously assumed. The fivefold atoms are a bit more intricate because they have very diverse local environments, and they have higher stability in some cases, and this is what explains why we can have a structure which has a few defects, why that structure is more favorable than a completely fourfold bonded WWW model. And that is because there are some fourfold atoms up here which are on their own quite unfavorable, whereas there are some fivefold atoms which are a good bit lower. So it is more intricate than is seen. Everything is tetrahedral. Right. So one thing is making accurate simulations and getting good quality structure models. But as chemists, we want a bit more from these methods. I think we want them to be flexible. We want them to be able to predict some structures that maybe we haven't seen before. And this is a line of research that I think is quite interesting, where we're trying to bring together the exploration of space and the fitting, and to use that to predict new types of structures. So this is a somewhat naive question, where I'm saying, can I make a fit? Can I fit a potential for just randomized atomic positions without knowing about any crystalline phases? So I'm randomly putting atoms in simulation cells and doing single point calculations for that. And I've sketched it in this cartoon. It's going to be a really, really rough potential, but I can use this thing to do structure searching. So what I'm doing here, I'm using something very similar to the ab initio random structure searching that Chris Pickard and Richard Nees at Cambridge have developed with DFT. And I'm using the potential here to drive the same kind of search. I'm going to find some structures. They're not yet perfect, but I get something that I'm feeding back into my reference database, and I'm making a new version of the potential, which now includes lower energy points. And I do that a couple of times over, growing my database as I go. And then I'm gradually exploring the crystalline phases on that potential energy landscape. Now, of course, this is a very simple cartoon that I've drawn, but let me show you proper data. This is elemental boron, so one of the structurally most exciting elements, I think, and rightly called a challenge. So we've got initial seed, some of these structures here, very high up in energy initially. So we're making some wild guesses as to where atoms might be. But then gradually, as we iterate and as we gradually feed data back into the potential, not just is the energy of the points in our database going down step by step, but also the prediction error for the known crystalline phases is improving as we go along. And then after a couple of iterations, when we're satisfied that the potential can find things such as alpha boron, we're going to put them in the database. Of course, at that stage, the prediction error is going to be very, very low. But that allows us to then fit a potential which can describe, for example, all the different crystalline allotropes with high accuracy. And so in sort of analogy to the AIRS technique that has been around for a very long time and very successfully used, I'm calling this gap-driven random structure searching, so gap RSS, and all the work that follows is based on that initial proof of concept from 2018. So another example from from a Faraday discussions paper, elemental phosphorus, again, searching over a couple of iterations and adding structures to the database. And this is quite an interesting example, because here we're finding orthorhombic black phosphorus after a couple of iterations, and you see how the prediction error massively drops after the potential has discovered this structure and has added it to the reference database. You also see that you do need to have put it in database at least once if you want to get reliable energy volume curves. So here we see how the potential is sort of circling in on the structure, but only now has it found it, and we then need to do even more calculations to refine that. You see it in the lattice parameters, which are approaching the right thing. You can do the same thing at high pressure. Now for phosphorus, it's I'd say it's semi-exciting, because everything either turns into the arsenic type or the simple cubic structure. But I think this is an interesting perspective in the future for looking at high pressure phases, where structure searches have often been extremely helpful. And there's no reason. I'm back, sorry. So a few examples from that initial paper, because you can now use that potential to do crystal structure searching and to look for possible new structures. So here are a few candidates, very simplistic ones, but they are somewhat related to types of nanorod structures that people have made experimentally for phosphorus. There are a few predicted 3D structures here, so the chemists will recognize this one here is the same anion network as in lithium germanide. So according to the Zinkel-Clem rules, you'd have this kind of network in the 3D structure, and that fits quite well with what we expect. You can do much more with these potentials. This is something that's just come out using an approach that Chris Pickard and his colleagues have initially proposed on decomposing structures into fragments. So you can do this in various ways. This is the structure of fibrous phosphorus. So this is experimentally known. You can dissect it into different types of building units. This is really using just the nomenclature from solid state chemistry. You can find variants of fibrous phosphorus which either have this building unit or the other. But also you can then do a very large scale search and find that actually there's a lot of new structures that are based on the very simple P8 cage, which is shown here. So here are some examples where we find initially there are these sort of chain structures coming out of the search, and they're a bit high in energy. But then if you go to lower structures, you find these single and double helix structures all made up of the P8 cage. And I think it's a quite nice demonstration in a sense that you can do very large-scale structure searches at very much reduced computational cost. The other direction of this research is that not only can we use the potentials to search for interesting things, but we can use the algorithm to build potential fitting databases in the first place. And this is work done mainly by Noam Bernstein, who has really masterfully coded up all this framework, where we say, okay, we now again do a random initialization. We guess lots of structures. And one of the key aspects now of this work is that we're adding a selection step. So we're not just blindly feeding back all the structures, as I've done in my very initial attempts, but now we're selecting the most representative ones. And then we're building our database using that. We're fitting potentials gradually as we go along. And then iteratively, we improve the database, again, using a multi-step selection procedure to make sure we're only picking those structures which are most relevant. You can see here again, so we've revisited the problem of alpha boron, and you can see, in fact, if you just randomly add points back into your database, it takes quite a lot of time to do that automatically. If you include a proper selection step, which is the best one is shown here in purple, you can see how gradually the algorithm does discover this quite interesting structure. You can then do that for a range of materials. So here's a proof of concept for carbon, silicon, titanium. So we've got an insulator, semiconductor, metal, and all the energy volume curves are automatically learned within 2,500 small cell DFT iterations. So you can really run this in a couple of days quite efficiently. Now you're going to say, okay, I know what graphite looks like, I know what diamond looks like, but what we really want is to cover the configuration space broadly, right? We want to include configurations which are maybe not initially thought of, but we need them to get a proper description of the potential energy surface. Now, this is a distance map based on SOAP similarity, where basically the distance between the points tells you how similar these environments are. And I've put carbon, silicon, and titanium in the same plot. And you can see how we're going from low coordinated graphite-like structures to tetrahedral allotropes, high pressure silicon, and then if we go up in coordination numbers, we've got MEGA and HCP titanium. We also got a bit more weird structures here, which we need to get robust potentials. And I think this is a direction possibly to build these databases in a rather automated fashion. So the third part of this, when I'm saying, how is this all useful for chemists? I think one exciting aspect is that these potentials are really starting to solve practical problems. So they can be applied to functional materials, and we're starting to do that. Let me go back to carbon once more and say a bit about carbon surfaces. So these materials are used for coatings, for electrodes, and that means that we need to understand what is going on at the surface of the individual sample. And if you take a simulated carbon structure and you just cut it in half, then of course you're going to cut bonds and you're going to create these unfavorable under-coordinated environments here. And then what you normally do, you take the samples and you anneal them for a while and you heal these dangling bond defects. That is actually done in experiments, but of course over longer times and at lower temperatures. But it does help us to do these surface reconstructions and to see how do the surfaces stabilize themselves. I've shown you before this massive simulation cell with 10,000 atoms, and that's one direction in which you could go. But you could also say, can we build smaller structure models that we can then use for example, for DFT calculations, for looking at reactivity and for looking at other properties at these surfaces. And we can use, again, this is the SOAP similarity, in this case, how similar the structures are to diamond and to graphene. So it shows us, the diamond-like regions in the slab center light up here, and the graphite-like structures light up at the top and bottom of the slab. And we can use that to quantify what kind of system size do we actually need to do reliable structural modeling of these surfaces. And it turns out 216 is actually a really good compromise. Now, once we've got these lots of different small structure models, we can use them to study reactivity. Now, you've seen that the carbon potential itself is for elemental carbon, but if you take carbon samples in a realistic environment, you're going to expose them to air, to moisture, to all sorts of reagents. So you want to see sort of what are other elements doing at the top of the surface. So here's an example. This is something that was done together with Lars Pastewka and Richard Jana in Germany. So they've put progressively more hydrogen into these slabs using tight binding and grand canonical Monte Carlo. And we're basically tracing, as we add more and more hydrogen to the systems, how the sp3 count in the surfaces goes up, because the hydrogens are saturating the under-coordinated environments. We end up with about a third of hydrogen in the sample, which is the experimentally known concentration for TSCH, as people call it. Aside from hydrogen, we can look at oxygen. We can also look in more detail at the different environments, so we can really tease out from these simulations which types of environments are going to be important and which aren't. We can look at oxidation. So in this case, I've used DFT-based simulations because of the much more complex processes that are happening. So you see here surfaces that are gradually being heated in contact with oxygen. If you heat it too much, you see this carbon monoxide here flying off, so you're starting to burn your sample. But you're going to recognize here these types of local environments that are really reminiscent of what the organic chemists identify in molecules. So this is, I think, a way of looking at what is happening on the atomistic scale at the surface of these very complicated materials. Another thing you can do, and this is work that's really being led by the Alto group, so I just want to flag it here. We can use these structures to predict spectroscopic fingerprints. So in this case, this is X-ray spectroscopy predicted for various types of carbon atoms in our surface slabs, and we can then go and build libraries of fingerprint spectra, both for X-ray photoelectron spectroscopy, but also XIS. So you've got this wider range of different signals using the SOAP, but also some electronic kernels to cluster and to find the most representative environments, and to take all that data and put it back into a fit and to resolve experimental spectra, which are often very, very hard to assign. Another type of carbon materials that's very interesting is those more porous forms, which are used in energy storage. So if you have a low density carbon, you have pores where you could put ions in there, whether that's in supercapacitors or batteries. This is some work done together with Claire Gray's group at Cambridge. So again, I say, can I make a library of small structures, and are those useful to study electrochemical questions? So how to make these? So we make a lot of amorphous carbon systems, and this is an idea that was already introduced several years ago by Nigel Marks and his colleagues. You take a low density AC structure and you bake it for a while. So you see here, and then every 100 picoseconds you remove sort of chain structures, and with that protocol you end up with very, very high sp2 counts. So you get graphitized structures, and in fact, you can say this is another project. This was done by Shanxing Wang from Xiamen University, who was visiting us, and he looked at all this parameter space here in terms both of density and in terms of local ordering, which I quantify here by the count of different odd rings in the structure. So if I'm going across all this parameter space, I can say where are the most representative structures, and what does that tell me? In batteries, what I want to know is about the voltage filling curves, right? So I go and again I'm using DFT here with a technique that's quite similar to the random structure searching. So randomly putting ions, or Xiangxing is doing that, putting randomly atoms in these cells and relaxing lots of them, and then you can go and compare the energies can be converted to voltages, and the lithium filling can be converted to this coordinate here, which tells us how much lithium is going inside my structure. And that can be compared with experimental voltage curves. Another thing we can do is look at the electronic charges on the atoms. So there's been some work going back both on lithium and sodium ion batteries, where it was found that if you store more and more lithium or sodium in these materials, there is a certain shift in the NMR signal, which tells you there are some more metallic-like environments. And we can study that now with DFT calculations. This is a histogram of charges putting more and more lithium into our disordered carbons. And you see at low lithium filling, almost all the atoms are in a lithium plus-like configuration. Then if you add more and more lithium, you're starting to see these more metallic environments. This fits quite nicely with what people have observed in NMR. And of course, if you have lots of these structures, again, this is something I want to emphasize. If you use your potential to do some of the modeling work, for example, generating these structures here, which takes very, very long and is very efficient to do with, for example, a gap or any other ML potential, you can then take these structures, plug them into electronic structure analysis, for example, using DFT, or in this case, we've used the lobster code, which was just released in the latest version. So you can go to this website here if you're interested in that. And I think it's an interesting perspective to combine the structures that you've obtained from the purely structural modeling with electronic structure analyses. In fact, there's another thing that I want to highlight in this context, and that I was super happy about, is that it's not just myself and my colleagues using these structures to do new science, but because we're, of course, providing these structures online, and you can download them from the supplement of the papers, there are two very recent papers I just wanted to highlight. So this is entirely independent from what we are doing. So I told you about these surface labs for pure TAC, and this group of authors recently went much beyond that and started using, among other things, these carbon slabs for very comprehensive DFT analyses, looking at different scientific questions. I've told you about these nanoporous carbon structures that we've generated. Again, this is a paper that came out recently. I think that's quite exciting, and it shows that there is a potential impact of these methods in a wider range than just those people who make the potential itself. So these things do enable quite exciting further work. With that, I'd like to come to my summary. I tried to convince you, and two of my claims here were that machine learned potentials are both accurate and flexible, and that makes them increasingly popular simulation tools, and they are really fast. And therefore, they're beginning to solve real-world problems, and by that I mean questions that are interesting to physicists, material scientists, and to inorganic chemists such as myself. And finally, most of the work I've presented to you here from my fellowships at Cambridge, which was about molecular dynamics with ML force fields. Beyond that, I think there's a lot of potential for using these tools to quantify and also to understand all the links between the structure, the bonding, and the physical properties in solid state materials. And this is something where we're quite excited over the coming years to be able to work on. I wanted to just add a couple of recent preprints. I didn't have time to talk about all of this work, but we have some things in these different areas that you're very welcome to look at. And with that, I'd like to close and say thank you. Most of all to Gabo Jenny, who has hosted me for almost 4 years at Cambridge, and who turned from being my Humboldt host to my mentor and my long-term collaborator. I'd like to thank the masters and the visiting students who contributed to the work, carbon materials. Big hat tip to Miguel Caro and the colleagues at Aalto, who have been working with this for a long time. The other colleagues worked with us on amorphous silicon crystal structure prediction. So all these, and there's lots more that hasn't even been fitting on this slide. I'd like to thank the funding agencies that made all this possible and have allowed me to build up this kind of work. Those that funded my own positions and those who made the computations possible. Special shout out again to HPC Europa 3. So this is an exchange program that you can use to go to other European universities and do research. And I've benefited from that program really a lot, both as a visitor and as a host. So I really recommend that. And yes, with that, I'd like to go back to the summary, and I'm very happy to take questions. Thank you again for the invite, and thanks for listening.
Thanks a million, Volker. So this is, I guess, so it's where everybody's clapping, right? So it's happened just virtually. And so thanks a million for the talk. And I guess we take questions now. So so there was a question actually that came very early on from Rohit Goswami. So I apologize if I butcher the name. And the question is essentially, I think, go back when you were describing how you integrate two-body and three-body in the construction of the machine learning potential. And the question essentially is how many neighbors are required for a Gaussian fit to be valid?
So yes, so this is this kind of combined model that we're making. There are two different things. So one question is, how far out does your descriptor go? How many environments do you have to take into account? In this case, we've used a cutoff of 3.7 angstroms, which gives you the first and the second peak in the pair distribution function. So it includes the next nearest environments. And everything up to that cutoff is being included, which gives you a dozen or so of contacts probably. In the three-body term, the cutoff is shorter, so we only want the closer atomic environments, and then the SOAP again goes out to about 3.7, or in other potentials it goes out to 5 or 6 angstroms maybe. In terms of how many configurations do you need to fit these potentials, so a typical size of a reference database is on the order of a couple thousand. And that really spans from very small unit cells. You could have maybe a primitive cubic unit cell, which is just a single atom in the cell, ranging up to about 200 atoms in the cell. You don't normally have to go much beyond that. So there is a computational cost in generating reference data. But I think the larger cost nowadays in terms of time and effort is really thinking carefully about what do you want to include in the database. And that's one of the big challenges in the field, I think.
Yeah, so there is a question which I think is more or less on the same vein than the one before, and from Rajashri Tiwari from my own group, and he's asking, what happened to the quality of a fit for a rather large cutoff radius? And the question is, how does one choose an appropriate cutoff radius?
Great question. So in principle, you would hope that the larger you make your cutoff, the better everything gets. And in fact, one of the primary limitations of this approach is the fact that it is fitted to short-range descriptors. It turns out in practice, there's often a limit at about 5 to 6 angstroms from what I've seen. There are ways of including longer range interactions. There's some that colleagues of mine are working on. We are. There is work by a group. So Jörg Behler and his group showed early on how you can include long range terms, basically fitting separate neural networks for the electrostatic types of interactions. There are long range force fields by Stefan Gödecker and colleagues who look at really just the electrostatic contributions in very ionic materials. But for what I'm talking about here, so most of these SOAP gap models up to date, so the carbon potential, but also the so Gabo's group has developed a silicon potential, which is quite powerful, or a potential for tungsten and iron, and these are usually 5 angstrom long. And it turns out that for those systems, you get good accuracy with that finite cutoff. You're never going to capture everything, but it is a good trade-off in terms of being computationally feasible and in terms of still giving you good results.
Okay. Okay, I don't see any other question in the chat box, so maybe in the meantime people are thinking. I'll ask a question myself. And I was thinking about your random search, combining gap with random search, and I was wondering how crucial is the choice of the prototype when you do the random search. So in other words, so those potential, if they are asked to predict something which they significantly never seen before, so it's very far, they can go completely bananas, right? So they don't have any way to interpolate. So I just wondered, actually, can you bias somehow the initial set of prototypes, or your data set initially so standard that it actually doesn't really matter?
So it is important how you do the sampling at the beginning. So how you choose those points which are higher up on the potential energy surface. And some of these approximations that we use in the search are really, as in Chris Pickard's and Richard Needs' AIRS approach, where you say, for example, you're going to use a hard sphere cutoff. You're not going to place two atoms extremely close to each other. You put some reasonable constraints and you use some symmetry. And in fact, NOAM's code makes use of many of these reasonable approximations. In that paper that I'm showing here, we've searched with unit cells up to 24 atoms per cell. So of course that means if you'd be looking for structure, which is as you say, very, very weird, you might not be able to find it immediately. You might want to tune the parameters. If you know you're searching for something which is very, very strange. The truth is that for lots of materials, such as these carbon and silicon and titanium allotropes, you do get quite far with up to 24 atoms in the unit cell. And I think that one of the goals here was really to show that you can do this in a quite efficient manner. If you knew you were looking at a very, very complicated material, there are those even elemental structures, boron, manganese. Then you would be making this a bit larger. But in terms of getting something robust, which is a starting point then for expanding it and adding more data, I think that is a pretty good deal in terms of number of evaluations that you have to make. And the other thing I should add is that we are doing this kind of thing, but there's also other groups who are very successfully showing how you can explore phase space with these relatively small structure searches. And there seems to be a consensus now that if you just use single point calculations, it makes the process really quite efficient. So there's really nice work also by other groups that goes in that kind of direction, building reasonably small databases.
And maybe just a quick follow-up question. So say for this example of your 24 atom cell, what about the volume of a cell? I mean, is this you try different volume, or actually you constrain the volume for the initial search?
So the initial configurations are in some reasonable volume range. You can modify them a little bit. You could use, and we haven't done this here, you could use, for example, very high pressure. If you wanted to know the phase diagram at 100 gigapascal, you could just set the initial pressure to that value. But normally you're going to do something, again, you're going to use settings which are reasonable.
And so maybe I'll ask maybe the last question, and then if there is no other, I think we might close. I mean, so how does the complexity of this method scale with the number of element that you have in your, so because you show a lot of single elements or carbon, silicon, and so on. I mean, so it's just one element double the number of material in the training set, or it's significantly more complex than that?
So yeah, this is one of the interesting directions. I think if we want to go to lots of questions in solid state chemistry, where often you have 3 or 4 components, there's nothing in principle that's stopping us from putting more species in. In fact, we've made a potential this was led by Felix Mukano and Stephen Elliott at Cambridge Chemistry, who made a potential for germanium, antimony, tellurium 225, so this phase change material, where there are 3 components in the gap. Other groups have shown ML potentials with actually many more species in the fit. So not just you're looking at molecules, but also materials. There are some studies with very, very complex compositions. In some sense, it is a question of whether you want to describe the entire ternary system. If I have GST, do I want crystalline germanium? Do I want liquid tellurium and all these things? Or do I want a certain composition? If I said, I want to study a given ternary alloy at a specific composition, that would narrow down the kind of space that I have to look at. So again, this requires what I think people call expert or domain knowledge. So you need to basically know about the system that you want to study.
Yeah, thanks a million. Okay, so I don't see any further questions, so I guess we can close here. So I would like to thank you again for the really insightful and wonderful talk. And no, there is another question. Sorry, sorry. So Vincent Chung is asking, how does the number of DFT evaluation using in the gap random search, random structure search compared to other algorithms, say like USPEC, so I guess genetic type of, I guess this is a question come up a lot, right? How genetic algorithm compare with random structure search?
So this is something that is actually being explored by other groups that have coupled USPEC or Calypso, so these other structure searching techniques, to ML potentials very successfully. I do not want to make any claim on random structure search being more effective or less effective than genetic algorithms or others. I think they're all able to give us interesting structures. They're all able to run global searches. And much as you could combine the same approach that we've presented here, you could do the same thing really with neural network potentials, with MTPs, and I know that both types of potentials have been used very successfully for structure searching, coupled to different exploration schemes. So I think the most important bit is just this idea of combining the two, and then you use whichever approach you prefer. They all have their advantages and disadvantages, I think. But again, I'm not going to judge one over the other.
Okay, so I guess with this one we can close. And as I would say, thanks a million again for the talk, and thanks everybody out there for watching. And we will come back next week. Thanks a million.
Thank you very much for having me. Thanks.